Hello students, good morning everyone. Yeah, a mistake. Just I have scheduled two sessions. I've started the session another one. I hope now you guys are getting the waves concept. Instead of starting this session, I have started the 12th. Right. Welcome everyone. Right. So today's concept is Doppler effect. It is one very simple concept, but very important in especially competitive point of view and also in board point of view, right? In one of the sections already we have discussed briefly what is Doppler effect and some a few different cases. In another section we have not started this concept yet. So let me start from the beginning of this concept. Doppler effect. Doppler effect. What is Doppler effect? Doppler effect says that whenever there is a relative motion between a source of sound, I'm using the word here sound, but you guys have to keep in mind that Doppler effect is applicable even for light also. That time you have to relate this source for the source of light. Okay, so we are completely confining it to sound. So whenever there is a relative motion between the source of sound and observer, the frequency of the sound heard by the observer will be different from the actual frequency of the source due to relative motion between the source and the observer. This is called Doppler effect. This is called Doppler effect. So you can write down as a statement, even though just we're dealing little, a little more towards comparative point of view preparation. Just you need to have an idea about the conceptual part as well. So write down the definition part of Doppler effect. So write down what is Doppler effect. Doppler effect. Doppler effect. Can write it as uh, the change in frequency. So you can, if you see different books, different ways of definition statements you may come across again, because I am pointing out this is some of our students are having the habit of referring other books. Just to don't think that this way is correct, this way is correct. The conceptually you have to follow. Okay, the change in frequency, note down the change the change in that's change in frequency of sound heard by the observer heard by the observer heard by the observer due to relative motion between due to relative motion between this means between due to relative motion between source and observer, source and observer. The change in frequency of sound heard by the observer due to relative motion between source and observer is called Doppler effect. Is called Doppler effect. And briefly, we consider three different cases here. What are those three different cases? Is when we can observe the frequency of the sound observed by the observer will changes is usually just we consider a first case. Let us consider a first case when both source and observer both are at rest. When both source and observer both are at rest. Both are at rest. We can both are at rest. Then how the so what do you call the frequency of the sound observed by the observer? If let us try to look into briefly conceptually. Let us usually consider the source on left hand side, and observer on right hand side in many of the cases. In some cases, we interchange the positions also for the convenience. For the convenience, there is a source. Source means it's something like a siren. You have a bike. If you if you press the horn button, it will give the horn. There's a bike horn. You can consider as the source of sound. Okay, the horn or a whistle. You can, if you are whistling, you can consider that whistle as a source of sound. If a sound wave is, if the source produces sound, so sound wave is coming or continuous sound waves. So I'm talking, sometimes it may come, it may not come continuously. Just a second guys, just I'm getting that call, let me attend it. Get back to you guys. Yeah, when both source and X guys. Uh, excuse me guys, just there was a call, right? When both source and sound, both source and observer is at rest, that means this is source. It is not moving. Say for example, if you consider a bike is at rest, so velocity of the source you can consider as zero, and observer. So if you consider that you are the observer and you are also at rest, observer is also at rest. Then whatever the frequency with which the sound is produced by the bike or a car or a bus or a train, whatever it is, it will so let us consider the sound is traveling with a velocity v. Velocity of source is vs, velocity of sound we will represent it as v. So sound velocity, source velocity, don't confuse. This vs means source velocity. Vs doesn't mean that sound velocity. Sound velocity is v. If sound is traveling with velocity v towards right or towards the observer who is at rest, then the same with what frequency the sound is coming, the same frequency he will hear when he is at rest, when both are at rest. So that is if the frequency heard by the observer, if you take it as f dash, you can take, in this case you can say f dash is equal to f, that is when both source and observer both are at rest, when both are at rest. Yes. So that is the first case. That is the first case actually to understand. Here, before going ahead with the next cases, I would like to give you guys a small idea of a sign conventions. So write down here how to consider the sign conventions. Sign conventions. Briefly, sign conventions of what? So the sign conventions for velocity of source, velocity of observer, and even velocity of sound as well. So if first point, if the velocities of observer and source are in the direction of sound, then usually we will take these velocities as positive. Okay, so write down some different just if you observe different books, they will give different ways the terminology. Otherwise we can also consider that if the if they are moving towards positive x direction, we will consider positive, negative x direction negative. Like this we also can consider. Okay, so you have to consider this carefully depending on the situation. You may consider this way or that way. This way you guys have to follow carefully. So what is that? Note down this sign conventions also quickly. The yeah, first thing, um, write down first point as you have to stick to this. Okay, if you are following this particular sign conventions. So the direction of first point, write down the direction of v, that is velocity of sound, is always taken from source to observer, is always taken from source to observer. Source to observer, that is the first point. You can consider, if it is source, this is observer. Sound is always traveling from source to observer. That is what you have to consider. V is always from this to this, right? The second point is, if velocities of v naught and vs, if v naught and vs, if v naught and vs, where v naught is velocity of observer and vs is velocity of source, uh, if v naught and vs are in the direction of v, then they will be taken as positive. Direction of v, then they will be taken as positive, or simply you can say positive. V naught and vs are taken as positive, they are in the direction of v. As third point, if v naught and vs are in opposite direction to v, if v naught and vs are in opposite direction to v, then they will be taken as positive. Then they will be taken as negative. So these points you guys have to remember. That means here, in this case, the other way what you can understand is, let us consider this is positive x direction. Positive x direction, this is negative x direction. That way also you can consider. I'm giving an idea, other idea of how to deal with them is, if if we consider in positive x direction, so if s and source and observer both are moving in same direction, we have to take this as positive parameters, otherwise negative. So that means in opposite directions means negative. And hence here we have to make use of the concept of relative velocity as well. You guys have to remember the concept of relative velocity, especially in one dimension, two dimension concept also we will make use in one of the special cases. Now let us consider the second case. That is, when the source is at rest and observer is moving. When source is at rest and observer is moving. Observer is moving. So here, based on this discussion, I will give you one general formula. You guys have to follow that hereafter while calculating mathematical expressions. When the source is at rest, say this is source, so Vs is 0, and of course it is producing sound, so the sound wave is traveling with the velocity of v, and here observer is there. Observer is moving, and here we will consider two further special cases. Case 1, if observer is moving away from the source, means in this direction, that is first case. And the second case is the source. This is source, so Vs is 0, means he is at rest and is producing sound waves. That's where sound is moving with the velocity of v, not Vs. Sound is moving with the velocity of v. Okay, whereas observer is moving but towards the, so this is observer velocity, here it is observer velocity. Right, in these cases what you have to understand is, we know the frequency. We are discussing about the frequency. The change in frequency observed by the observer due to relative motion between the source and observer is called what you call a Doppler effect. It's called Doppler effect. So the frequency when the sound is traveling with the velocity v, of course it is having some frequency f, but the frequency heard by the observer, let us express it as f dash. Okay. What we know is frequency is equal to frequency in general is nothing but velocity. So frequency of sound is nothing but velocity of sound by its wavelength. Velocity of sound by wavelength. Whereas uh, frequency heard by the same sound by the observer, we call it as relative, what you call apparent yeah, the frequency of dash, we call it as apparent frequency in this case because it is not actual frequency. uh, we can also call it as apparent frequency. F dash is equal to velocity of a sound, the velocity of sound heard by him by the wavelength. Here wavelength will consider as the same only. But velocity, actual velocity of sound is v. But because of the relative motion between this, his velocity sound is moving in a positive direction. Observer is also moving in positive direction. So the relative velocity between these guys will be taken as v minus v naught. So by comparing this, we can write by dividing this, we can write f dash by f will take f dash by f is equal to f dash will be v minus v naught by lambda. F is v by lambda. Lambda is cancel. We get f dash by f is equal to this, or from this we can say f dash is equal to v minus v naught by v into f is the frequency of sound heard by the observer. We call it as apparent frequency of sound heard by the observer when it's moving away is a v minus v naught by v into f. I hope you guys have understood this clearly. I said based on this we'll give a generalized formula after this case. Whereas if the observer is moving towards the stationary source, so in this case, so frequency of actual sound is v by lambda, whereas f dash frequency of sound heard by the observer when it is moving towards the source means in opposite direction. You will take this as what is that, negative sign, right? So relative velocity of these two will be you can consider here relative velocity will be positive, v minus of minus plus v naught by lambda I have to take. Then if you consider the ratio, of these two, then we get f dash by f, and hence direct relation I'm giving you guys here. F dash is equal to v plus v naught by v, the same way the lambda value is cancelled into f. This is called, sorry, into f naught. F dash is equal to this is f only. This is the apparent frequency of sound heard by the observer when he is moving towards the stationary source, I hope it is clear for you guys. Once it is clear, then other cases you can understand very easily and I can follow simply. Right? Yeah. So the same way you can get for the other case, that is when observer is at rest and source is moving. Right? Okay. So let us see that case as well, and we can what do you call, combine the effects, and we can give the what you call generalized formula. Then immediately we can do the numericals. Let us see the third case as well here. Third case. First case is when source and observer both are at rest. Second case is source is at rest and observer is moving. Third case, let us say observer is at rest and source is moving. When observer is at rest, when observer O is at rest and source S is moving. How I mean in what direction? Let us see in sub cases again. First case, the source usually will consider, on left side, observer will consider on right side usually. So observer is at rest means VO is equal to 0, source is moving. In the first case, source is moving towards the observer. When S is moving towards stationary observer, stationary observer stationary observer means here, so actually it is producing sound So his source is moving to velocity of Vs, and along with, actually sound is also moving in the same direction. Is producing, source is producing sound, sound is moving towards the observer, and source is also moving towards the stationary observer. These two velocities are in this direction, provided when he is observing the sound, he is observing the sound. These two are moving in the same direction. These two are moving in the same direction. How we'll get here? This is the same way just as like in the previous case. The what you can understand here is, just if you consider this, the actual frequency of sound is, actual frequency of sound is supposed to be what? Actual frequency is nothing but velocity of sound by wavelength, whereas the frequency heard by the observer due to the relative motion is f dash. F dash is equal to, because the source and sound is both are moving together, both are moving, so you can say that this is equal to V, the frequency heard by this, because of the relative motion between these two, V minus Vs, because both are moving in the same direction. Relative velocity will be minus V minus Vs. Simple concept. Relative velocity of relative velocity of two velocities moving in the same direction is difference between them, opposite directions, plus, that's what you have to remember in simplest form, by lambda. So now divide this to f dash by f, and lambda gets cancelled, then we'll get f dash is equal to, actually here, uh, oh, wait, guys. So frequency of sound and the frequency heard by what do you call, observer. Here, when you say observer, even a small correction here, we are not considering this velocity. One small correction, guys. Yeah. We are talking about here, this f dash is the frequency heard by the observer. That means with respect to observer velocity, velocity of sound with respect to observer velocity. So velocity of sound is coming, he is at rest. So with the same velocity only he will observe, but frequency of sound with respect to the source, with respect to source is earlier, source is at rest, so I have considered simply as this component will be different actually. Now this will be, what is that? When he is both are moving in the same direction, then we have to consider this component will be minus Vs, my V minus Vs, this component. Now if you take the ratio of these two, you get f dash by f is V by lambda by V minus Vs by lambda gets cancelled, V minus Vs comes here in denominator, V minus Vs, V by V minus Vs into f. This is the apparent frequency in this case. Whereas in the next case, when the source is moving away from stationary observer, when source is moving away from stationary observer, that is, let us consider, this is source, this is observer velocity is 0, and when it is producing sound wave will travel in this direction towards the observer with velocity v, but source is moving away, that means Vs is this direction. So you can see here f, frequency of what? So here we can say frequency of sound with respect to the source. These two are moving in opposite directions, right? So the relative velocity will be what? V plus Vs by lambda, and hence f dash, frequency heard by the observer. Frequency heard by the observer is as when he is at rest. So you can say that V by lambda. So f dash is equal to, f dash by f is equal to, then what will get? The same procedure, V by V plus Vs into f. So what does this mean if you observe these equations? Here, actually, when, just let us compare these cases briefly. Let us compare. When both are at rest, the frequency observed by the observer, that is apparent frequency we call it as f dash is equal to f, means the same frequency he will hear, the same frequency of sound he will observe. Whereas when the source is at rest and observer is moving, when the observer is moving away, when the sound is, when a whistle is blowing here but the observer is moving away, means the frequency or pitch of sound he will, the intensity of sound will reduce when he is moving away and away, right? That is what you can observe here. F dash is equal to V minus V naught by V. So as is moving away, V minus V naught, if you consider, the total value will be less than the actual value. So that is called as apparent frequency. Here you can say apparent frequency is less than actual frequency. This is actual frequency F. So apparent frequency is less than actual frequency. Whereas in this case, when they are moving together towards each other, so here the source is giving some whistle, a sound, and he is moving towards it, towards the source. He is to feel like the pitch of the sound is increasing gradually when he is moving towards the source, a siren, right? That means the apparent frequency, the frequency heard by the observer is apparent frequency will be greater than actual frequency. This is what you can conclude from this. Whereas similarly, in the third case, when observer is at rest and source is moving, when observer is at rest, source is moving towards the stationary observer, even though observer is at rest, but source, which is giving the siren, continues the sound beep like zzz, like that, and he is moving towards the stationary observer. So observer will feel the sound effect is increasing. So here, if you observe in this, denominator is decreasing. V minus V means denominator decrease means total value will increase. So from this you can conclude that F dash will be greater than F. That means apparent frequency will be greater than actual frequency. Whereas when the source is moving away, and the whistling source, when the siren source is moving away from the observer, means say for example, the best example is we are standing in a bus stop or a railway platform. In the previous case, we are standing in the railway platform. A train which is giving a horn and approaching towards the station, you will when it is far away, you will hear the sound but less sound. By the time it is approaching the station, you will feel the sound, the sound effect is increasing. That is what is apparent frequency. When after approaching the station again, it is without stopping, it is moving away from the station. When it is moving away, you will feel like the sound effect is decreasing, the pitch is decreasing. Okay, that is the meaning of it. So in this case, F dash, that is called apparent frequency, will be, as denominator is increasing, it will be less than the actual frequency. These are the conclusions you can draw from this. So by concluding all this, I will give you the general formula. Write down here now the general formula. General formula. While giving general formula, I will add one more term. If only sound is blowing and it is reaching the observer, we'll consider velocity of sound only. We will consider velocity of sound only. Whereas if the medium, if the sound is traveling in air medium, that medium called air is also blowing. Air is blowing in the direction of sound. It will take that sound waves faster and reaches the observer. So if is a source, sound is moving in this direction. If a wind is moving with velocity v in the same direction, it will drag this sound towards the observer. Whether he is at rest or moving away or moving closer, it will drag the sound towards him. Whereas this wind is blowing in opposite direction, it will delay the sound to reach him. So this point also will consider while considering the general formula. So in the general formula, I am giving you that apparent frequency of dash is equal to V plus, that is velocity of sound plus velocity of the medium, that may be here velocity of air, or in case of liquids also you can consider liquid medium or gaseous medium, any medium. Velocity of the medium, velocity V plus velocity of the medium plus or minus V naught by V plus Vm plus or minus, I have to take minus or plus Vs, provided what does it mean is when the wind blows in the direction of V, when wind or medium, let us take it as wind, or there is the subscripts you can consider as a W, then you can clearly can remember velocity of wind, velocity of wind in gaseous medium only. If you consider in some other medium, liquid medium, you have to consider water velocity or something liquid velocity like that. So you have to remember this. So when wind blows in the direction of, in the direction of sound, in the direction of sound, whereas apparent frequency can be given as f dash is equal to V minus VW, or you can say Vm, velocity of medium, plus or minus, here you can take V naught by V minus VW minus or plus Vs. Here also you can take minus or plus. According to the sign conventions, accordingly I have to take into, this is f dash, right? This is f dash is equal to this into f actual frequency. Here also f dash is equal to this into f. So this is a apparent frequency in terms of actual frequency, so it will be less than or greater than that. That's what you can understand. So this is the expression for general formula for apparent frequency when wind blows when wind blows in opposite direction to that of that of sound. That means sound velocity we will consider v. So these points we'll have to consider, right? So this is one of the very important relation you guys have to keep in mind. The next point I will give you here is few more sub cases are there. Those things we will discuss along with the numericals. Now let us try to work out some numericals. Open your volumes, level 1, exercise 1. Let us do one or two questions in level 1, exercise 1, question number 36. Level 1, exercise 1, question number 36. Question number 36. So what is given here and what you are asked to find? It is given that the speed at which the source of sound should move so that stationary observer finds the apparent frequency equals to 11 by 12th of observer means observer is at rest, stationary means 0. Towards stationary observer finds that the apparent frequency equals to, apparent frequency means f dash equals to 11 by 12th of the original frequency, that is f. So for this condition to satisfy, what should be the velocity of a source? So when it is moving towards the stationary observer is the question. So you can draw pictorial representation for this also. Source is moving with the speed vs towards an observer v is at rest. So what should be the, so that for the frequency relation to be satisfying this, for this frequency relation to be satisfied, what is the velocity of source in the question? So we know f dash is equal to v plus or minus, what is that, plus or minus the medium velocity also in single formula, right? Here the velocity of wind is not given, so you can take it as 0. Plus or minus v naught, observer velocity is 0 by again here you can consider v plus or minus wind velocity is 0 by velocity of source. What is the velocity of source when it is moving towards the observer, stationary observer means, or you can take is moving in positive x direction, so relative velocity will be v minus vs, right? This is into f. So we are given f dash is equal to 11 by 12 f, right? So from this you can say f dash is 11 by 12 f is equal to v by v minus vs into f. So here f gets cancelled out. Then here if you observe the options, they are given in terms of v, so you have to find out vs in terms of v. So this for implies 11 by 12 is equal to v by v minus vs, implies 11 v minus 11 vs is equal to, if you bring, we want vs, if you bring the vs this side, it becomes yeah. So what is, just let me cross check once again the data here, that speed at which the source of sound should move so that the stationary observer finds the apparent frequency equals to 11 by 12. 11 by 12 means, is it greater than f or less than f? You can observe here it is less than f. That means here you have to understand one more point here. Yes, it is f dash is less than f means it should be moving not what is this, toward, is less than means should move, the source should move away, not towards. Towards means should be minus, but when it is moving away, then only the frequency will decrease. So that means you have to take this positive term. This should be, you have to take positive term. This will be positive term. So this should be positive, right? This is simple observation. You have to take a note. Now this implies 11 Vs. 11 Vs is equal to 12 V minus 11 V is V. So Vs is equal to V by 11. V by 11. So question number 36 option. If you see the options, option V by 11 option will be the correct one. Vs will be V by 11. That's it. So this is how you guys have to just work it out. Question number 39. What is given here and what kind of how to use this Doppler effect in understanding this kind of questions. Let us see. It is given that an engine is moving on a circular path of radius 100 meter. In a circular path, an engine is moving in a circular path, of radius 100 meter, with with a speed of 20 meter per second, with a speed of speed of 20 meter per second. What does it mean? The engine is moving means what? Let us see the question completely, then again once again we will try to observe the data. The frequency observed by an observer, standing stationary at the center of a circular path when the engine blows a whistle of frequency 500 Hz is when the engine blows a whistle of meters per second. The frequency observed by an observer will be called as apparent frequency. So f dash is what? Frequency observed by an observer standing stationary at the center of, this is observer position. Observer V naught is 0. Standing stationary at the center of the circular path when the engine blows a whistle of frequency. Actual frequency is how much? 500 Hz. So here the source is the engine. We can call it Vs is relative velocity. The relative velocity between source and observer will be such that in normal cases or in tangential case, or you can say this, if you see the distance, there is no change in relative position. The change in relative, if relative position changes, then relative velocity will comes into picture, right? Relative position is not changing, right? Even though it is here and here, the relative displacement is constant. So relative velocity between these two is zero. Velocity of observer and relative velocity of source and observer are zero. So we can conclude that apparent frequency, there is no relative position, change in position means no relative velocity, and hence when the relative velocity is zero, that means both are appear to be at what you call at same positions, relative positions, we can say. So f dash is equal to f. That is the simplest form considered as. So f dash is equal to 500 Hz, because relative relative velocity of observer and source are zero, because the relative positions are not changing. Relative positions, of course the direction changes also. The relative change in relative velocity is zero. Relative position is zero, so change in relative velocity is also zero. So frequency, the same frequency you will heard. That is one of the way of understanding this. There are different ways you can understand this, guys. This is one of the way you can understand, right? The similar thing you can also analyze by observing one more special case I will give you. Okay, we'll see this now, that special case. Give you one special case now, then we'll go ahead with the other questions, few more questions. Say we call it as a transverse Doppler effect. What is that? A transverse Doppler effect, or when when the when source is crossing the stationary observer, or observer is crossing the stationary source, like this kind of questions will come across based on this. We call it as transverse Doppler effect. So note down here, transverse Doppler effect. Transverse Doppler effect. So what it says is, if the source is moving in a direction, making an angle, some angle theta, arbitrary angle theta, with respect to the observer. Then how to find the apparent frequency, let us try to understand. So write down as a first case, when source is moving in a direction, in a direction by making an angle, let us say some angle theta or phi or anything like this, an angle theta with respect to the observer. Then what will be the apparent frequency? Let us again here we'll consider some different cases, we'll see those. So to understand this, let us consider a pictorial representation of this. Say there is an source, you can consider this as a siren, something like a siren which is giving sound, and this is a horizontal line, and here is somewhere observer is standing stationary, right? When the source is giving sound, is supposed to, the sound wave is supposed to travel in straight line direction towards the observer, right? But when he is moving in this direction, provided at an angle theta with respect to this, right? Who is moving here? Well, a source. This is Vs. Then a component with actually the sound is traveling in this direction. So the velocity of sound with respect to source velocity, if you want to know. So the component of velocity of source in this direction we will consider as Vs cos theta. Vs. Say if you draw a perpendicular line from the observer onto this line of motion of source, so that at some point, if you say this is in point A, is supposed to cross this point and reach some other point B here, but this point, if you mark it as C, at this point, if the source is making exactly an angle of 90 with respect to the position of observer, and if it crosses and is moving, okay, again depending on the velocity direction, maybe the velocity of this line making an angle of same angle of theta with respect to the horizontal or the direction of propagation of source, then we can say that apparent frequency, the same relation we can use, apparent frequency f dash into f will get v minus vs cos theta. Here v and vs cos theta is traveling in the same direction. Vs cos theta, not vs cos theta, traveling in the same direction to reach the observer here with respect to the direction of motion of the observer. He is situating at a position which is making at an angle theta. In that such cases we have to take this relation vs cos theta, so we have to consider this kind of cases while doing the questions based on this, right? So that is when the observer is when the source is moving from this position. So we can say when he is moving like this, this Vs as theta, if you observe, theta will be increasing gradually. As it increasing, this will decrease gradually. That means denominator will increase, and hence apparent frequency will. So if this can say that overall, you can say that the apparent frequency will decreases gradually till here. Then here onwards, apparent frequency is observed to be actually with respect to these positions, apparent frequency is observed to be increasing. That can be given as at C. You can say apparent frequency is this is at when he is at A and is moving towards this, whereas apparent frequency is observed to be exact into F is at B will come across. We have to keep in mind these things. Okay, there is another point. There is another kind of case also will come across in this as yeah, it is shown the data is exhausting, so I'm checking whether one more case let me give you. Yeah, that is if you can consider this as like this, it may be extending this way also, a kind of a crossroads or not, irrespective of this. So a car is moving in this direction with velocity v1, and a car is moving with velocity v2 in this direction, provided, but when I say this is, if this is acting like a source, then this is acting like an observer, then then you have to consider that. Are you getting any disturbance in the voice? Just if you are getting any disturbance, drop a message in the chat box. The velocity, this is observer, this is source. So if this is at an angle of theta 1, this is at an angle of theta 2, then you have to consider that sound will be moving in this direction is v1 cos theta, and a component of the velocity, component of both are moving here, right? So when the component of velocity of the observer along this direction is v2 cos theta 2, v2 cos theta 2, this is cos theta 1, then the apparent frequency v right. So here, if you observe, what is that velocity of when this sound and this are moving in the same direction, you can consider, yep. So observer v plus or minus observer velocity by v plus or minus source velocity, right? This is sound velocity. Observer is moving in opposite direction. We have to take it as v plus v2 plus v2 cos theta 2 divided by source with respect to sound source is in same direction, so minus relative velocity of this same direction velocity is minus, right? V minus v1 cos theta 1 into f. This formula you have to use to find out the apparent frequency heard by the observer in this kind of cases. Just keep this in mind. The next very one simple case I would like to give you here is what should be the apparent frequency heard by the observer if it is if the sound is reflecting from an obstacle and coming back. We call it as echo. We call it as echo, right? Yes, it is something like buffer. I'm observing something like buffering. I hope you guys are getting that much clearly, right? So this, how can you understand this is, the concept of echoing is, we can call it as when a moving source produces a signal, a sound, and it is reflecting from a stationary object or stationary wall or stationary mountain, and it is coming back. So, and the same sound is observing by an observer which is in the direction of source, then it is called as an echo. How it appears like, the how the apparent frequency appears like, and is there any difference between the actual frequency and the apparent frequency, and if so, beats will be produced. What will be beat frequency? Let us see briefly. So let us consider there is a car. There is a car. A car is producing some siren, so that sound is more sound. If you consider is to understand in this kind, what you call to calculate the apparent frequency in this kind of cases, you have to do this in two stages. First stage is you have to consider this as observer, stationary observer. Then after coming back this sound, it will reflect back. During this position, you have to consider the velocity is moving in this direction, and this will be the driver or observer here as this, and this will be the source velocity. That is second stage. And one more point you have to imagine here is, you have to imagine that this after reflecting back the sound is coming, means you have to imagine that, you have to assume that the sound is coming from a car who is behind this wall or behind this mountain with the same velocity but in opposite direction. So in this kind of cases, what you have to consider is the direct velocity. You will get, just if you see, when the car is a direct frequency, if you consider the direct velocity of car in opposite direction, so relative velocity of this two will be taken as plus by v minus vc. This will be, actually this will be the source source, or this will be observer. So you have to